Differential and integral operations 1. Consider the two-dimensional scalar potential function phi of xy is equal to x cubed minus 3y square x. Part A, make a plot of the equipotential contours for 3 positive and 3 negative values for phi. Alright, so here is a mathematical code. We have the function written here, x cubed minus 3xy square, and we're doing a contour plot from x equals minus 5 to plus 5, y equals minus 4 to plus 4, using a temperature map as our color function. So when we execute this, we find that the phi, our scalar potential, can be represented with these constant potential curves, which are our contours. So these are phi is equal to 50, phi is equal to 100, minus 50, minus 100, etc. And then we can have intermediate values here. The problem was actually asking for 3 positive and 3 negative values for phi. We can also see that here 3 positive and 3 negative values, so we can have, for example, phi equals 1, phi equals 8, phi equals 27. These would be the equipotential lines, and minus 1, minus 8, minus 27, these would be the equipotential lines. Part B says find the gradient of this scalar potential function, find gradient of phi. So how do I calculate gradient of phi? It is EI hat, the gradient operator, del phi, the derivative with respect to xi. So this would be, if I open this up, it's a summation. It's going to be EX hat, the derivative with respect to x of the scalar function, which is x cubed minus 3y square x. And then I have the y component, EY hat, the derivative with respect to y, del y of the scalar function, x cubed minus 3y square x, and then there could be a z component, but since there is no z component, plus 0. So the last term is 0. So we can now write gradient of phi. There is the gradient of phi as, now if I take the x derivative here, this will give me 3x squared minus 3y squared. So it's going to be 3x squared minus 3y squared EX hat. And as for the y derivative, for this one it is 0, for this one it is minus 6yx. So this will be minus 6yx EY hat. That's the gradient of this scalar function phi. Let's look at part C. Show that the gradient of phi field lines are given by setting 3x squared y minus y cubed equal to a series of constants. So how do we find the gradient of phi field lines? So that's the question. For the field lines that we will draw, we have a requirement that the slope dy dx is equal to the gradient of phi's y component, gradient of phi y component, divided by gradient of phi x component. All right. Now we already know what the y component is. It is minus 6xy. We have calculated above in part B. And the x component is 3x squared minus 3y squared. So this must be equal to dy dx. Alright, so if I multiply this with dx, so cross multiplication, and this part with dy, I will obtain the following. Minus 6xy dx minus 3x squared dy, and then I will have plus 3y squared dy is equal to 0. So this is minus 6xy dx is equal to 3x squared dy minus 3y squared dy, but then taking them to the left hand side, minus 3x squared dy plus 3y squared dy. Alright, so if you have the differential of a function f of xy equal to 0, that means we're looking at the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. That is basically minus 6xy dx plus 3x squared minus 3y squared dy. Now we can read the partial derivative with respect to x. So del f del x must be equal to minus 6xy, which tells us that if I take an integral with respect to x, f of xy is of the form minus 3x squared y plus a function of y. So derivative with respect to x is 0 for this one. For derivative with respect to x here, it's minus 6xy. And then the partial derivative of f with respect to y must be equal to we can see here 3x squared minus 3y squared let's check that here. So this was actually minus 3x squared plus 3y squared. So there's a minus sign here, plus sign here. So taking it down here, we have, therefore, del f del y is equal to minus 3x squared plus 3y squared. All right, so that's that term, and this one is this term. All right, so this tells us if I take an integral with respect to y, this must be of the form minus 3x squared y plus y cubed. The derivative will give me 3y squared plus a function of, possibly a function of x. All right, so let's put these two pieces of information together. We have minus 3x squared y plus g of y is equal to minus 3x squared y plus y cubed plus possibly h of x. So this tells us that h of x must be 0. There is no h of x, and there is a g of y, which is y cubed. So we can read our function now, f of xy. So f of xy is equal to minus 3x squared y plus y cubed. It's a differential form, which is del f del x dx plus del f del y dy must be equal to 0. That means this is a constant, or in other words, we can multiply this by -1 and say 3x squared y minus y cubed must be a constant. So when we plot these field lines, this is the function that we will plot, and we have obtained the end result by multiplying this answer by -1. Constant multiplied by -1 gives another constant. So going back to the question here, this is what we were supposed to show. The gradient of phi field lines are given by setting this function equal to a series of constants. And part C says plot 6 representative gradient of phi field lines. Be sure to indicate the direction of the field and comment on its magnitude. Now going back to our mathematical plot, the x component is gradient of phi, the first component x, gradient of phi, the second component y, and then we can do a vector plot, and this basically shows us our field lines. And the color scale indicates the magnitude, so you can see that close to the origin here I have low magnitude, and going further away from the origin I have a larger magnitude. The alternative way to plot this is, instead of using the color, the density of the field lines. For example, when this function f of xy is equal to a constant, so these plots here are basically those plots, and now you can see that the density of the lines is increasing as I go further away from the origin, and basically I have nothing right in the middle, so the magnitude is going to 0 right in the middle here. Okay, so we have two ways of plotting the field lines. We can show the field lines setting this equal to a series of constants, and now the density of the field lines basically shows us the magnitude, and also we could use a color scale to represent the field lines magnitude. So here our temperature map basically shows us that in the middle the magnitude is getting close to 0, and going further away we have basically larger magnitude in these regions. So this is basically where we have red. Part E, find the divergence of the gradient of phi, the divergence of the gradient of phi vector field, and show that your field lines of part D agree with this divergence. What is the divergence of the gradient of phi? Let's calculate this. Divergence of the gradient of phi. This is the divergence of what we have found in part B. So let's copy our answer from part B. 3x squared minus 3y squared ex hat minus 6xy ey hat. That's our gradient. Now we're taking the divergence. So we take a derivative with respect to x of 3x squared minus 3y squared. And then we take a derivative with respect to y of minus 6xy. So this will give us the derivative gives us here 6x, and this derivative gives us minus 6x, which is 0. So we find that the divergence of the gradient of our scalar potential phi is 0, as expected. So what does this mean? All the field lines entering a region leave. Divergence is 0. It's not a source or sink of field lines. implying that there are no sources or sinks of field lines. So we can observe that these field lines are always perpendicular to the constant equipotential surfaces, which are equipotential surfaces. And then we also know that the divergence is zero, which means wherever you look at in this plot, there is the number of field lines entering and leaving are the same, which implies that there are no sources or sinks of the field lines. Okay, so in this problem, we have looked at the scalar potential function x cubed minus 3y squared x. We can make a plot of equipotential contours by setting this equal to a set of constants, 3 positive and 3 negative values, or we can use a mathematical code. A contour plot will do the trick for us, and we can see where these equipotential surfaces are. And in part B, we calculated the gradient operator is EI hat del del xi, which is a summation. So it's EX hat del del x plus EY hat del del y applied to this function gives us our gradient. And in part C, we were asked to show that the field lines are given by setting this function equal to a series of constants. So for that function, dy dx, the slope must be equal to gradient of phi y component divided by gradient of phi x component. So writing this and recognizing that the function, the differential form of the function is zero, so the function is equal to a set of constants. But what is that function? We can write the differential form of a function with two variables, x and y, partial derivative with respect to x dx plus partial derivative with respect to y dy, and this gives us two possible solutions, and here we recognize the h of x part is 0, and the function is minus 3x squared y plus y cubed is equal to a constant. Its differential form, the derivative of the constant is 0. Or multiply it by minus 1, we get the answer suggested by part D of the problem. Okay, so we were supposed to show that these should be equal to a series of constants. Then we plotted field lines. Basically, x component must be gradient of phi's x component, y component gradient of phi's y component, and those are the field lines, and its direction basically is indicated here. The magnitude is indicated by the color of the field line. So very low magnitude, close to zero, almost zero magnitude in the middle. In part E, we showed the divergence of the gradient is zero, implying that all field lines entering a region must exist. There are no sources or sinks of field lines. And we can also see the same answer here from a different plot for the function values being 1, 8, and 27, f of x, y equals 1, 8, 27, and also equipotential surfaces 1, 8, and 27. And you can see that these field lines are crossing perpendicular to the equipotential surfaces, and the magnitude is really becoming zero in the region close to the origin.